Hey guys, welcome back to my YouTube channel. It's 2022. You want to hit that subscribe button and turn on your post notifications so you know every time I post. Alright, hey guys, told you that I was going to complete this paper for you all. So, welcome back to my YouTube channel. So, this is question 2 for the 2021 physics paper. As I said, I'm doing them in parts because I'll be going through a bit of content as well. So it's not like your regular past paper review. I'll be doing full papers later down in the year, closer to the exams, you know. And look out for the marathons that I'll be running. I am thinking about doing them in April. So yeah, I'm going to start registering in February or later to the end of February. So look out for what I'm doing. It's going to be epic. So let's get into the paper, right? So 2 wants you to define each of the following terms. As I said before, they get terms, it's best you know how to define them. Of course, you can always define terms by telling me that telling me the formula, right? So I'm going to give you 2 definitions, which would be like perfectly fine or acceptable. So the moment of a force is the product of the force and the perpendicular distance from the pivot. Alright, so that's fine. Also, you can say the moment, so this is 2, of a force is the measure of a force's tendency to cause a body to rotate. I'm kind of jumping off here, but stay with me. I can't do that, bro. To cause a body to rotate, right? So that's also acceptable. So yeah, bro. Alright, bring that down a bit so it's not as messy. Nice. So basically the first part here that I mentioned, the moment of a force is the product of the force and the perpendicular distance from the pivot. That is the formula. So the moment of a force is equal to Fd, and in some cases if you're given an angle, you can have the moment of the force being equal to F sine theta multiplied by the perpendicular distance from the arm, you know. So yeah, let's see the other one. Oh, still have us defining terms, huh? I ain't bad. So center of gravity. Now the center of gravity, no brother, what is that? It is actually that. I don't think I write that bad, come on. So the center of gravity, right, is the point on an object where gravity, I don't even like using about the same word, but it's just It's practically the same thing. Gravity or weight, or the weight of the object, appears to act, right? Which sometimes is seemingly at the center, but as you're going to see in the next question, it's not always at the center. And I'm going to prove it with math. Now, it's quite easy for you to get something like this, but it's often, let's say, mixed up with what exactly the center of mass is. The center of mass is not the same thing as the center of gravity, even though they're closely related. Now, the center of mass is the mean or the average position where it appears that the mass of an object is concentrated. So, for example, if you had a square, right? If you were supposed to balance a square on a pencil, it would seem as though the mass is concentrated in the center because it's a regular shape, right? And it's given or assuming that the paper is the same thickness all throughout the course, along this, it's the same thickness, then we'd expect the mass to be concentrated at the center, and thus the center of gravity would be at the same place. However, if we're dealing with an irregular shape, I'm sure you did the experiment where you balanced it from like a retort stand, and then you marked where lines would cross and where the lines would intersect would be the point at which the center of gravity or the center of mass is concentrated, right? So even though they are seemingly the same thing, they are not, because the center of masses deals with the mass distribution of the body itself, while the center of gravity is where the force of gravity appears to act, or the weight of the object is concentrated. So as physics students, I know that you know the difference between mass and weight, right? Where mass is a scalar quantity, so it only deals with the magnitude, while weight is a force, so it is apparently, or let's say it is usually said that weight acts downwards. So, well, let's not say usually, it is that weight acts downwards, but we usually take downwards as negative. So whatever the scalar magnitude is of the force, it will still have a direction indicated by a sign. So mg, which is the force of weight, is usually negative whenever you're asked to calculate it like that. So you don't write your figures with the negative sign, or you don't have to. What you do is write the scalar unit saying that, say it is 5 newtons acting downwards, if that's the weight of your object, right? And even so, you don't even have to put acting downwards. If you say the weight of an object is 5 newtons, we know that it is acting downwards because weight acts downwards. So, whatever suits you or you're most comfortable with. Now, they want you to say 2 conditions necessary for a body to be in equilibrium. Now, for a body to be in equilibrium, let's say number 1, the forces have to be balanced, right? So if we're talking about moments, the total clockwise moment has to be equal to the total anti-clockwise moment. So the resultant force is equal to 0. So basically the sum of the net forces is equal to 0. If it is that there is a net force greater than 0, that would mean that your body would begin to accelerate, and thus the body would no longer be in equilibrium. Remember, equilibrium is the standard or the most stable state, where the object is most comfortable, right? So once there is a resultant force, a body will accelerate, and we can use Newton's law, third law, to prove this. And I like to use my little chair example. So let's say you're sitting on a chair. Probably should have drawn this better, but Alright, that look like one chair, right? Oh my god. Alright, so that's a chair. Kinda messed that one up, but I'm gonna tell you that I'm the best person for this job, you know. I think I'm making it worse, but hey, that's a chair, right? And let's say you have a person sitting on the chair. Now, whenever someone sits on a chair, their weight is acting downwards, right? So if this person, say, weighs 10 kilograms, then the force acting downwards is 100 newtons, assuming that we're going to use G as 10, right? Now, by Newton's third law, whenever a body A, which is this person, exerts a force on body B, which is the chair here, the chair or body B will exert an equal and opposite force back on body A. So A pushes on B with 100 newtons of force, right? Then B will push back on A with the same 100 newtons. However, it would be a negative 100 newtons force because it's in the opposite direction. So remember, the signs only tell you direction, right? Not necessarily it doesn't have anything to do with the size of or the magnitude of the force exerted, right? It just tells you that it is in the opposite direction. So you'll see that the chair will push back on the person sitting on the chair with that 100 newton of force, and thus the resultant force, right, would be equal to that 100 newton. Well, the sum of the forces would be plus minus 100 newtons, which would actually just be minus 100 newtons. And you'll find that the resultant force F is equal to 0, right? Now, let's say the chair is not able to... I should have used this as the negative 100. Alright, let's just do that then. Yeah, let's do that. Let's take downwards as negative. I didn't take that into account here. I just switched the signs because of the opposite direction. But it's not confusing. So let's say that the chair pushes back with only 90 newtons of force, this time upward, and we say upward direction is positive. So let's use it like that. So the sum of the net force, or the net force, would be equal to negative 100 newtons, meaning 100 newtons of force downwards plus 90 newtons upwards. So that would mean that our resultant force, now there will be a net force, will be 10 newtons downwards. Now, seeing that there is a net force of 10 newtons downwards, that means that the person is going to fall from the chair because that chair is going to break. The chair will not be able to withstand the weight of the person, so there will be an acceleration downwards because of that net force, right? However, let's say the chair pushes with 110 newtons of force, then that would mean that the sum of the resultant force would be equal to 100 newtons plus 110 newtons, which would actually be equal to 10 newtons, and that's positive. So that's telling us that there will be a net force of 10 newtons upwards, and that would mean that the chair will be pushing you upwards with a force of 10 newtons, more than what you're pushing down with. So that would mean that the chair is going to throw you in the air, so you'll accelerate upwards. So once there's a net force, acceleration will take place. So I hope that was clear. If you have any questions, just link it in or drop it in the comments below. So let me clean this up because I like space. Alright, so the second condition that I'll talk about is the resultant moment, right? The resultant moment has to be equal to 0 as well. So we talked about the resultant force and the resultant moment. So as I said, the anti-clockwise moment has to be equal to the clockwise moment, and thus that balances out. So anti-clockwise equal to clockwise, then if you're supposed to find the net sum, then it would be 0, right? So that would mean that if you had a greater clockwise moment than the anti-clockwise moment, then that would mean that the body would be swinging in the clockwise direction, and you don't want that. You want it to be in equilibrium. So in order to do that, you have to balance out the moment, right? So I'm going to give you another one for good luck. Number 3 is the line of action. So the line of action of the force and that force meaning the weight in this case has to fall within the base of the object. So basically, that's why for the most part race cars are made with very broad and very low bases, is in order to keep the center of gravity or the line of action to keep the line of action of the force within the base of the object. So if it acts downwards, then you want it to fall within the base in order for it to be stable. Now if you have an object that's tilted like this, the center of gravity still acts downwards, right? And thus it's no longer within the base, so you know that this body here is going to accelerate this way towards the ground, right? So it's going to topple over or fall. It's the same thing for an upside down triangle for the most part, right? It will fall, it depends on how you balance this, it will fall or topple over. So the best way to set this triangle would be this way, so it falls within the base, right? So yeah, let's look at the other question. So question C, what I like to do is underline important things from it, especially long. I don't do well with reading. Let's just say that I don't like to have a lot of bulky information because most of it is just fluff. So I like to underline to point out the important stuff and so that I don't get distracted, right? So figure 2 shown below in the diagram is a non-uniform wooden plank. That's good to keep in mind. So that would mean that this here is not in the center. It tells you right off the bat that it's not in the center, but we can prove it, right? It tells us that the block is 2 meters, the wooden plank is 2 meters long and it weighs 1000 newtons, and the plank is supported from the ceiling by 2 springs P and Q, and the plank is attached at a distance of 0.5 meters from each end. So that would mean that, let me edit my arrow because this isn't even the arrow that I wanted though. Let me see if I can find another one. Well, that didn't go as planned. Let's try that again. I should be able to edit the arrows though. I'll just use the line Cambodia and make it 2. Yeah, so that would make here, from here to here, 1 meter, right? That makes sense because 0.5 plus 0.5 here would be equal to 1, and we're told that the total length is 2 meters. So that would mean that between here would have to be, you know, the next 1 meter. So anyway, let's go down here and see what they're telling us. So when the plank is horizontal, the tension in the spring is 600 newtons. So spring P, it's 600 newtons. So I can just put that right here so I don't get mixed up. The question wants you to calculate the tension in spring Q. No, the tension in spring Q, it's not hard because it doesn't take up much working out. You can actually look at it and get the answer. The answer is 400, and I'm going to show you how the answer is 400. So basically, seeing that the object is in equilibrium, I'm sorry, the forces have to be balanced. So that means the total upward force has to be equal to the total downward force, right? So if that's true, total downward, let's write that first, is equal to the total upward, we can actually find out a few stuff. The total downward force is produced by W, right? That's the only thing producing a downward force, and that's equal to 1000 newtons. Now, the upward forces are produced by the springs P and Q, and that would mean that the total upward would be equal to 600 plus Q. So if we write out an algebraic expression for this, 1000 newtons would be equal to 600 newtons plus Q. Now, if we do a bit of transposition and make Q the subject of the sentence, Q is already positive, so all I would need to do is move the 600 here. So if I write 600 newtons, in order to get rid of it on this side, seeing that it's positive 600, I would have to subtract 600 newtons, right? And whatever you do on one side to ensure that the equation maintains homogeneity, meaning, you know, what the left side of the equal sign is equal to the right side of the equal sign, you have to do the same thing on the other side. So seeing that we just subtracted 600 from this side, we have to subtract 600 from this side as well, right? And that would mean that, give me a sec, 1000 newtons minus 600 newtons, that would mean that this would cancel, so 600 minus 600 is 0, so we're left with Q being equal to 1000 minus 600, which is 400 newtons. Therefore, the tension, I'm sure that should be an S, oh my god. The tension T subscript Q is equal to 400 newtons. So mark your words, I get your 2 marks, easy, and CSEC, I got a paper color. Congratulations. So the next part says, by taking moments about A, determine the horizontal distance from P to C. Alright, so let's go back up to this little diagram here. So P to C is from here to here. Alright, so we're supposed to take the moment from point A, and that would mean that they would want us to treat right here as our pivot. So they just made this a lot easier for you. So basically, that would mean that the moment, right, of this would be equal to the force, which is 1000 newtons, multiplied by, from this distance here, this would be x. Let's just call it x because we don't know it, it's an unknown, right? And we need to figure out what would be providing the total. This would be the anti-clockwise, so the total clockwise going up, right? So that would make the clockwise be equal to 600 times 0.5. Hold on. Yeah, I'm correct. Let me label this thing. I found this out as 400 newtons. This is our point, yeah. So another thing is the point Q here would be the distance from here to here, which would literally be 2 minus 2 minus 0.5, which is 1.5 meters. So that's one of the clockwise moments. Yeah, one of the clockwise moments. Then the other clockwise moment is provided by the 600 newtons force, which is 0.5 meters away. I literally marked it here, so 0.5 meters, which is right here. All right, so we can actually write out a little algebraic expression for this. So the total anti-clockwise moment, you can even write it out. So total anti-clockwise moment, yeah, just imagine that I wrote out the entire word, is equal to the total clockwise, right? And that would mean that the total anti-clockwise moment would be the force, the downward force, so Fw multiplied by the distance from A, which would be equal to the force P multiplied by the distance from A plus the force on Q multiplied by the distance from A, because they told us to use the moment at, take the moment at A. So the pivot is not at Q but rather at A. So that's my bad. I apologize. So the pivot is at A. So let's put in the figures. So the force or the weight is 1000 newtons, and it is 0.5 plus x meters away from that. We don't know. So it's 0.5 plus some distance away from it. And that would be equal to the force on P, which is 600 newtons, I believe, and P was 0.5 meters away from the pivot A, and if you add that to the force 400 newtons on Q being 1.5 meters away, I believe that's what I said. You can plug this into your calculator. I'm going to break it up though. Some of you might choose to expand this, but you don't have to. I am not going to, because that's going to be a longer process and I kind of want to finish the question. Okay, you have a little time limit going for you. So 600 times 0.5, which would literally half of 600, which would be 300, right? And 600 newton meters plus 1.5 of 400, which would be 4 plus 2, 600, I believe. So basically 1 plus half of 400, but put it in your calculators. It's 600, so I'm correct. 600 newton meter, right? And 600 plus 300 is 900 newton meter, being equal to 1000 newtons times 0.5 plus x. Can divide by 1000 on both sides, because what I want to do now is get as close as possible to x being by itself, right? So 0.5 plus x and 1000 newtons. So as I said, I'm going to get as close as possible to getting the statement to read x is equal to something, right? So I'm going to try and get rid of everything that is on the x side. So first things first, you have to get rid of that 1000, seeing that you're multiplying it by everything else. So seeing that we're multiplying by 1000, in order to get rid of it, we have to divide by 1000, right? And remember, I said whatever you do on one side, you have to do on the other side. So if you cancel that out, you're going to get 0.5 plus x is equal to 0.900 newton meter, I believe. And this here would be in meters, so 0.5 meters. And the newtons here would cancel newtons here, so I can take this out of my equation. So I'm left with 0.900 0.900, which is 0.9. Yeah, correct. So then if you realize what's happening now, we are actually adding 0.5 to x, and remember we want to get x by itself, so we want the statement to read x is equal to something. So in order to get rid of that 0.5, saying that we're adding it to x, or let's say 0.5 is positive, we'll subtract 0.5 from that side of the equation. So what you'll find is you'll have 0.5 meters minus 0.5 meters plus x is equal to 0.900 meters. Whatever you do on one side, you have to do on the other side, right? So we have to subtract 0.5 meters on this side as well. So the statement that would be left will have us read it as x is equal to 0.9 minus 0.5, which is supposed to be 0.4. So 0.4 meters. And big up yourself. We get the answer for that. Usually when I do my exams, I write a final problem statement so that my examiner doesn't have to, search through my bag of calculations to find out what my exact answer is. And it leaves no room for them to mistake what my answer is, because marks are given where marks are due, right? So yeah, them not have to ask Chris what my answer be, because me just write it in my end problem statement. So my end problem statement would read that the horizontal distance from P to C is 0.5 meters. So that's all I would write at the end. So the horizontal, yeah, I make this a habit because I don't want them to mistake anything, especially because I'm not so sure if my handwriting is up to par. So distance from P to C is equal to 0.4 meters. Yeah. So I like tonight's little thank you, babe. So yeah. Now they want you to state why the center of gravity is closer to P than the point Q. Now, first of all, the question, in the original statement, they told you that it was a non-uniform wooden plank, so you would expect that the center of gravity would be closer to one of the springs than the other. And this is so that the total clockwise moment provided by the springs would balance out the total anti-clockwise moment, or let's say that the other way. The clockwise moment is provided by the downward force on the beam. So let's say this is our beam. Boom, 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 boom. The weight is bringing it down. So it would provide a moment going that way. While, oh no, I'm not incorrect. I'm not incorrect at all. It doesn't even matter, which one you take as clockwise or anti-clockwise. Just know that both are the top ones are providing either clockwise or an anti-clockwise, while the bottom force, the 1000 Newton, is providing a different moment. So yeah, so basically what's on top is supposed to balance what's on the bottom. So basically that 1000 Newton there should balance out the 600 and 400 newtons forces at the top. Now if you work that out with a little bit of math, I can prove that what I just said is true. So let me go over to my whiteboard to prove this. So first let me write out the answer. This is the answer that I would put, to be honest. So the center of gravity is located closer. I feel like that's going to look like foolishness. Oh, that's fine. To the point P than the point Q. Thank you very much. So that the total clockwise moment balances the total anti-clockwise moment. All right. Of course, these questions shouldn't take it this long because it ain't that much. But as I said, I'm going through content as well, so that's why these videos are like 30 minutes long. But I think we're going in good time. So let me move over to the whiteboard. Give me a second so that I can actually explain this to you, right? Alright, so I brought this over to the whiteboard and ain't this looking fancy and this looking rich. Alright, so basically if we treat points, the point right here, that ain't even visible. Like, I'm trying my best to find a color that is visible. Alright, let's use this yellow. These points can be treated as supports, right? They are, you can even think about it as like little pivots here. So it neither causes a clockwise or an anti-clockwise rotation because they're balancing each other out. No, if we were supposed to put the weight or the center of gravity at the exact center of the beam, that means that this would be, instead of 0.4 away from meters from P, it would be 0.5 meters away from P. And we can think about the total moment here at P to be equal to 0. So MP for right now is equal to 0. Now, if we continue to work that out, we know that the total moment, so let's say take the clockwise direction as positive and the anti-clockwise direction as negative. Let's keep that in mind for now, right? So if we were supposed to take here as the pivot alone, negate this piece for now, this would provide a clockwise direction, clockwise moment, while this would create a moment in the opposite direction. So let's put that into a little equation. So now this would be 0.5 meters times 1000 newtons acting downwards, right? And we want to subtract the moment provided by the spring Q multiplied by, we said that this would be 1. We said that it would be 0.5. So its distance away from the pivot that we're using right now, which is P, would be 1 meter. So, and the total moment would be equal to 0. Now, if we work this out and solve for MQ, given that we said that it's 0.5 meters away from P, right? This would mean that this would be 500 newtons minus MQ, which is equal to 0. And that would mean that MQ is equal to 500 newtons, which is not true. It's equal to 400 newtons. So in order for this to be 0.5 meters away from the pivot, or in order for this beam to be, say, uniformed and have a center of mass that is literally in the center of the beam, the force when the 1000 Newton force downward is providing that clockwise moment has to be the for has to be 500 newtons for the moment provided by Q to provide a moment opposite to the downward force, right? Or the moment provided by the downward force. Now let's plug in the value that we actually worked out, that 0.4 meters, and it's the same concept, right? So let's walk you through this again in case you didn't get it the first time. So the moment provided by P we'll call as 0, right? So as we said, the moment provided by P here is 0 because the pivot we are calling here the pivot, and that is providing support. So that's taking any turning force. Instead, that's the point at which it's going to turn. So now the total downward, so the moment provided by this downward force, which would be, this would be clockwise, would be 1000 newtons multiplied by the distance that we actually had, which is 0.4 meters, right? And that plus the total anti-clockwise here provided, which would be actually opposite direction, so it should be negative. So that would be the moment provided by Q that we don't know, multiplied by 0.6 meters plus 0.4, which is 1 meter. And the total moment at the P, as we said, is 0. So then 1000 multiplied by 0.4, it's 2/5, that's 2/5, 0.4. It would be 400 Newton meters multiplied by MQ, which is equal to 0. And thus MQ, the moment provided by the spring Q, should be 400 newtons, right? So we got back the same answer that we got here, which shows that it's valid enough for it to be closer to P rather than to Q. So yeah, and you can try this using a number that would indicate that it would be closer to Q, and chances are the force will change for P. So yeah, I hope you understood this. It took me a bit out of time, but I don't think it was bad. It wasn't bad. But yeah, revisiting the questions. So the tension in Q is 400 newtons because the total downward force has to balance the total upward force in order for the beam itself to be in equilibrium, as the question stated. And we use the moment at A. That means that we treated A as our pivot or fulcrum, and we calculated the distance from P to Q by basically finding the perpendicular distance or perpendicular arms distance from A to C and subtracting from A to P from that total thing. So basically what we had was a long beam and this would be the distance from A to C. We knew that A to P is 0.5. So in order to find this segment here, we basically took it from the total that we found from A to C. So I hope that was clear. So we basically got this right here. Nice. And the next question, we got 0.4. and they wanted you to state why the center of gravity is located closer to P than to Q, and it's to ensure that the total clockwise moment actually balances the total anti-clockwise moment, you know, given the forces that we had calculated at the top, and everything checks out. And remember, the conditions necessary for something to be in equilibrium are the forces have to be balanced, meaning there's no net force, because if there is a net force, then the body will accelerate, and the resultant moment, meaning the sum of the anti-clockwise moment and the clockwise moment, should be equal to 0. If not, then there will be a turning force. And 3, the line of action of the force, that is the weight, should fall within the base of the object. If not, it will topple over and thus not be in equilibrium. And the examples that I used was the race cars. The race cars are made with extremely flat or low bases, let's say low bases, and they are broad, so that while traveling at high speeds, the car itself is less likely to flip or topple over, because that would be disastrous, right? And remember the difference between center of gravity and center of mass. The center of gravity is where the weight of the object is concentrated or appears to act, while center of mass has to do with the mass distribution, so the average or the mean position of the concentration of the object's mass. And remember that the moment of a force is the product of the force and the perpendicular distance from the pivot or the fulcrum, and the moment of the force is the measure of the force's tendency to cause a body to rotate or turn. And it can be calculated using the formulae m is equal to fd, and in a case where you're given an angle, it's m is equal to f sine theta multiplied by d, which is the perpendicular distance, the distance of the perpendicular arm. Sorry. And so yeah, that was question 2. I hope you learned some content you can use it to study. Share my content with a friend. Go follow me on Instagram. My socials are linked in the description below, and if you haven't yet, please subscribe to my YouTube channel, drop a like on this video, and leave in the comments or connect with me on Instagram. Tell me what you want me to do next. If you're watching my video, you can always tag me on Instagram. I'll always repost. Thank you guys for the support. I appreciate it. So until next time, bye guys.